in the agenda, my talk is called Historical, Technological, and Statistical Aspects of Reproducibility. And I put a subtitle there, an alternative title, Framing Transparency in Research Issues and Opportunities. What my larger goal in giving this talk is to try and unpack this notion of reproducibility. We hear this word a lot now, and I'm sure all of you have experience with this, where you talk to a particular researcher and their understanding of what reproducibility means is totally different than if you talk to another researcher. And so I think what I'm going to do in my privilege of having the last position is try to unpack that so that we have framings that can work in the different disciplines and understand the different ways that we can be coherent about approaching these problems. I just wanted to also take a note and mention that I put my slides on my website, so particularly to folks online, if you want to follow along with the most recent version, take a look at my website, and if you want to go back to something, I hot link a lot of stuff in my slides as well. Okay, so I wanted to start with Merton's norms just as a touchstone for the discussion. These are, to some degree, still controversial themselves, and I don't put them out there like this is an agreed upon fact. But he did put, in 1942, put out 5 framing issues around what it meant to do science and how the practice of science differs from other practices that we might take on in our lives. And he mentioned 5 of them: communalism. Scientific results are the common property of the community, so we're doing research as scientists and our findings actually go out as common property to the community. Universalism, we can all contribute, or anyone sort of calling themselves a scientist and adhering to these norms can contribute regardless of race, nationality, culture, gender, and differences that science is agnostic towards. Disinterestedness. We're acting for the gain of the scientific enterprise rather than our own personal gain when we're engaging in science. And originality, scientific claims are contributing something new. And finally, skepticism, scientific claims need to be exposed to critical scrutiny before being accepted. And the reason that I put this sort of listing of the norms up here, I'm going to focus on 2 in particular: communalism, which I think actually when Merton published in 1942 is called communism, which sort of evolved into communalism, but I'll stick to communalism. And also skepticism. It's a little bit blurred out here, but skepticism is the source of transparency and the reason we have these issues around reproducibility and standards for what we're calling science. A lot of it gets traced back to our need for skepticism, and I'll talk a lot about that in the talk as well. Okay, so we've probably all seen stuff like this, if not actually all of these particular reports. I pulled these, I think they're all under a year old, certainly all under 18 months old, so this is stuff that's available and out there. You probably have saw in October of last year, 2013, How Science Goes Wrong, focusing on, among other things, but issues around reproducibility. And it might be a little difficult for you to read, but in Science there's an editorial called Reproducibility, Nature, announcement regarding our irreproducibility, that they're exhorting us to, we must try harder in our research. And then NIH tackles irreproducibility. So this has certainly become something that there's a very broad-based interest in, and they're all using this word reproducibility. I also put an LA Times article up there that science has lost its way at a big cost to humanity, they're telling us. And it goes on to talk about these issues of verification and reproducibility in the scholarly record. So it's reaching out actually into the public at this point. So let's unpack this, what I just called a credibility crisis in science. I think a frame that I have found useful, and I put it out maybe for critical scrutiny, skepticism, maybe you'll find it useful, is I split this idea of reproducibility into 3 different groups. And the first one I've been calling empirical reproducibility. So I've put the editorial reproducibility, Nature's must try harder, and so on in this group. So what that refers to me are issues that are arising in the practice of science, the dissemination of science, that are traditional, empirical, long-standing problems we've had. So these are issues about reporting the procedures you go through, say, at the bench, in the wet lab, so that others can actually be skeptical about your work and understand what you've done. So the reason I pull that out is I want to compare this and contrast this with what I'm calling computational reproducibility. So this is all these scientific methods and tools that have been introduced probably over the last 20 years and are changing the way that we think about the process, practice, and our dissemination and evaluation of science that stem from issues around computation. So I'm going to outline this in a little more detail, but these are, in my mind, new. So these are new things that we need to adapt to as scientists and in thinking about the scientific method. They require different solutions and different thinking than the older, more traditional concepts around reproducibility. Okay, different from those two, but also I think useful in framing issues around reproducibility is a notion of statistical reproducibility. So I'll talk more about that one as well, but if you think about things like experimental design, do you have the power to even detect the effects that are in your data set? And if you don't, you wouldn't necessarily expect that to replicate, for example. So a host of issues under statistics and methodological causes for irreproducibility. Okay, so let me go back to my historical frame and think about traditions in the scientific method. So we've had two branches for hundreds of years. I'm sure you're all familiar. So the first one is the deductive branch, so we include in there mathematics, logic, all of our deductive reasoning. The second one is the empirical branch, and this is really kind of inductive reasoning. So we have our statistical analysis of controlled experiments landing solidly in the second branch of science. And there's lots of talk in keynotes and grant proposals, solicitations, and editorials in science about new branches of the scientific method that are arising due to these technological changes, which I'm putting under that rubric of computational reproducibility. So these get called variously the third branch of the scientific method, the fourth branch of the scientific method due to large-scale simulations or data-driven computational science. And so there are these assertions that all of these changes in the practice process of scientific discovery are actually leading to new branches of the scientific method. So my argument is that computation presents only potential third and fourth branches of the scientific method. And let me explain why I say that. Oh, okay. So let's look at, if you look at, I just sort of looked around on the web for, the roots of these discussions of third and fourth branches. And you probably can't see it in the small blurry text there, but you can see from the HTML that this is a pretty old workshop. So this is an old NIST workshop from 1995. And I pulled out the little piece of text there I wanted to focus on. It's common now to consider computation as a third branch of science besides theory and experiment. Now remember, that's 1995, and this is just common, and we all know that. And many of you are probably familiar with this edited volume, The Fourth Paradigm. I believe it was published in 2009. And if you just look in the preface, they say the book is about a new fourth paradigm for science based on data-intensive computing. So that's the entire focus that the authors are looking at. Okay, so let me unpack this technology a little bit further. So changes in how we do science are being driven from the technological stance, I think, from three sources, at least three sources. And the first one everyone's familiar with, that we've got tons of data. We have a national hobby of data collection. And we have this data-driven discovery, very high-dimensional data to work with that has revolutionized, actually, many fields. The second one, which I think is quite distinct, is our increases in computational power. So now we do our simulations, our complete, a complete simulation of an entire physical system. We can change parameters. We can run this again, opening up a whole new way of doing science, what types of questions we can ask and actually answer with these methods. So those are two, and probably you're familiar with both of these. The third one, I rarely hear people talking about it. I think it's just as important as the first two, and that's the rise of software. So now people who are doing science, generally speaking, almost always, they're also doing some kind of computational coding or implementation of software in the process of doing their research. And this has a corollary effect that deep intellectual contributions, real bona fide contributions to science, are now embedded in software and in code, and often only in the software and in the code. So I put a sort of screenshot of Lior Pachter, who is a professor here at Berkeley, and this is a YouTube movie of a keynote that he gave, and he says in there that the software contains ideas that enable biology. So his idea, what he's saying is these ideas are actually in the software, and this is, my argument's going to be for the rest of my remaining time, that this is a primary scholarly object that we need to be thinking about. Okay, so let's go back to our scientific method and think about how these changes are actually implementing what we understand science to be and what our standards actually should be. So we probably agree that the central motivation of the scientific method is to root out error. So we never are finding out the truth, but we are always trying to find out the truth. And what I'm trying to do as a scientist presenting my results is I'd like to convince you that my results are right, or as right as they can be. So hence Merton's skepticism and notions of transparency, so you can really understand if I've made mistakes or if there's something we should improve on or dig into further. So in the deductive branch, standards around doing this is the proof. You wouldn't think of publishing a mathematical result without including a proof for people to check. In the empirical branch, there are analogous standards, so we have an entire machinery of hypothesis testing, appropriate statistical methods, and then we have a very structured way that we communicate this in the methods section. So analogously to branch 1, you wouldn't publish, I don't think you even could publish if you left the methods section blank. You'd get journal editors saying to you, you need to fill this in. Okay, so my claim about potential is that for the third and fourth branch, these computationally based investigations, or anytime really you're using big data, computational methods in your research, we can't elevate this type of research to a third or a fourth branch of the scientific method until we develop those comparable standards. And we've been at this about 20 years. There's been hundreds of years to develop these standards in the first and second branches, so it's not really a fair comparison. However, we've got our work cut out for us. So a little historical context. So when I was a graduate student at Stanford, so not Berkeley, my advisor was David Donahoe, and he was influenced by a geophysics professor at Stanford, John Claerbout, who I believe is emeritus now. And starting in 1992, or even I've been told anecdotally by students, 1991, John Claerbout stopped signing a student's thesis if he couldn't effectively hit return and regenerate the document, including recalculating the figures and so on in the thesis. And the idea behind this, although it conforms with lots of what we've been talking about today in this workshop, the idea was really to help new students who are coming into his lab get up to speed on the previous research and start producing original results. It used to take them 2 years, and 2 or 3 years, and it cut them down to like 2 or 3 weeks, being able to actually have these standards of reproducibility in his lab. So my advisor summarized Claerbout's approach to reproducibility when you are using computational methods. If you have digital data, if you've used a computer to do any of your statistical analysis in your pipeline, for example. So the idea is an article about computational science in a scientific publication is not the scholarship itself. It's merely advertising of the scholarship. The actual scholarship is the complete set of instructions and data that generated the figures. So this comports with my earlier idea of ideas being captured in software that are very important to science and that are scientific contributions in themselves. So I just want to take a note here and mention another sort of angle on thinking about reproducibility, and I think these are important distinctions to make. So you can imagine reproducing the computational steps in an experiment, starting from, say, the raw data that the researcher had, presumably in a digital form, and then going through those computational steps and arriving at figures and tables that actually were the basis of their publication. And this is an important and I think vital step for us to implement in work that uses computational tools at all, at research work. Sometimes I get a question, Victoria, isn't that kind of silly, because you're not actually making a contribution to science, and it doesn't serve anyone if I can hit return and come up with your figures. I haven't proved anything, and I can do this on stuff that's wrong too. Well, of course. And so let's contrast this with the re-implementation independently of the entire experiment. So I understand from your methods section what you've done, and I go out and say I collect the data if that's part of what you did. And then I re-implement, perhaps in software, your methods of analysis that generated your results. Okay, so this is a real scientific contribution because I've presumably either been able to confirm or provide counter evidence for your results. Maybe I uncovered mistakes or who knows what. But we'll never be able to reconcile the differences in our implementations without that first sort of hit return and regenerate, that transparency in that first publication. So even though it's not a scientific contribution to be able to sort of chunk through your steps and so on, this is an important baseline to think about for enabling transparency in the communication of scientific findings and reasoning. Okay, so I was wondering when I first started thinking about this issue, whether this is really all that important. Like, how digital has science become? You sort of hear about these things, but maybe this isn't even something that's particularly pervasive. Maybe it's a small minority of the type of research that's been published. So I looked at the Journal of the American Statistical Association, one of our flagship journals, and I went back to 1996, and I was interested in two questions. One, are they publishing computational work? Is this all proofs in mathematics? And if they are publishing computational work, can I get the code? So this is sort of very, very rough back of the envelope. You know, I sort of had a very low bar about code. But what's notable, I think, here is by 2006, vast majority of these publications had a computational component, and by 2009, everything is computational in JASA. So there may be a proof, but they've done a simulation or implementation or something that's computational. And even by my generous standards, in 2011, the most I could get is 21%, even talking about or giving me some kind of assurance that they thought access to the code was an important part of the research that they had done and where I could actually get this. Okay, so I also found John Ioannidis' 2001 publication where he looked at 500 papers and found for 9% you could actually get raw data files. And so we don't have much transparency in the way that I was talking about it from raw data, even just chunking through the steps and getting those output, the published output. Okay, so I'm not going to talk about it today, but to come, I analyzed, this is actually very similar to John's work that he was talking about earlier. I analyzed publications in Science, and I have a rough estimate that about 27% that are being published are reproducible in the steps that I can just, in the sense that I can follow through the steps and get the similar results as were published, substantially similar. Okay, I wanted to talk about two little pieces of research that I had carried out to try and understand this issue. So, speaking of journals, I was curious about how journals had actually started to take on this issue around data access and code access, or whether they had even taken it on at all. And so actually, let me just go to the journals one. And so. Sorry. Okay, and so what I did is I chose three sections in ISI classifications: statistics and probability, mathematical and computational biology, and multidisciplinary sciences. So I ended up with 190 journals, and I looked at what their policies were with my students in 2011 and 2012. So I was also interested in the rates of change of those policies. And so we broke our evaluation of journal standards around data sharing and code sharing into 5 groups. So it's required as a condition of publication, and there may be exceptions, for example, patient confidentiality and so on. The journal says it's a requirement, but probably will publish, or may, it's not binding, like they'll go ahead and publish your work in any event. There's language in there that leads you to believe this is encouraged. However, it's not something that they're going to enforce for publications. And in the language, there's an implication that you're expected to be sharing data. And then, of course, the journal could not mention it. So I was actually surprised by how high these numbers were. So in absolute values, they're not that high. But when you think about the fact that in 2011 and 2012, this is still a relatively new topic, we see about 10.5% going to a little over 11% for requirements on data sharing, and a jump of about 2% to 6% in this requirement but not enforced. And then 21% down to about 18% with some kind of language around encouragement and implication up to 3%. So that gives us, in 2012, about 62% that weren't addressing the issue actively in their author guidelines. So I thought that was quite remarkable. For code sharing, the story is a little bit different. So much lower rates across the board. And this 3.5% you see with the requirement that was unchanged, those are actually code publication, like software journals, so you would expect they would have requirements around software access. Encouragement was, it went from about 10% to 12%, and implied we got about 2% by 2012, giving us about 79% that didn't mention it. So sort of faring worse than data, however, it's still non-trivial. And so this is something that there's growth and journals are taking on. Okay, so just a few findings from this study is that the action in journals happens at the high impact journal level. The lower impact journals seem to be less comfortable demanding more of their authors, and we really saw the biggest changes happening among the high impact journals. And there was more in this study that I don't have time to present, but if you have supplemental materials policy, you tended to have a data access policy, and open access didn't seem to impact whether or not you had data or code access policies. And as we could sort of see here, data supplemental materials policy, they're much in advance in leading code policy. So one thing I also wanted to mention in this study, I was interested not just in, say, what journals were doing, but how researchers were actually reacting and what incentives actually came to bear on researchers. So in this study, I looked at everyone who had attended NIPS, which is a machine learning conference, and I said, for your NIPS paper, do you have your data and code available with it? And if you do, why? And if you don't, why not? And I'll just pull out a couple of results. So here's when people did actually share their data and code. And by and large, you can see the reasons for sharing here, at least in the machine learning community, is really about the larger community and fostering good practices. So things like encouraging scientific advancement, encouraging sharing in others, being a good community member, tends not to be as self-interested. I mean, you get a little lower, you see things like getting others to work on the problem, increasing publicity, opportunity for feedback, and things that might be a little bit more self-motivated. When people weren't able to share, far and away the most important reason is not philosophical. They don't have an objection to this in theory. However, it takes a lot of time to share data. It takes a lot of time to share code. And that to me speaks to an incentives issue in the sense that researchers generally don't like writing their papers, and they go ahead and write it to publish it. So this is really, we're not rewarding sharing code, and we're not rewarding sharing data at this point. So I'll leave you to take a look at the other ones. I'll just notice the possibility of patents, legal barriers came up much higher than I actually thought they would, that this is a real barrier against sharing your data and sharing your code. Okay, so speaking of incentives that researchers are under, I also wanted to show you this plot. So on here are 6 physical constants that physicists were trying to estimate empirically. And I think what's interesting about this, so what's plotted here is the published estimate over time, for different papers. And so you can see that they actually do converge on a value, and I'm assured that it's the correct value, but the convergence isn't random, right? It seems to be somehow related to the previous results. So we have this, it looks like, at least in this case, we have this bias towards producing or publishing results that seem similar to what's come before. And so we sort of creep on to correctness in a biased way, in some sense. Okay. Okay, so one of the last things I'll mention is there's been a lot of talk today around standards and checklists and community members gathering together to try and understand how research data or software and information about their work should or could be shared. I was part of the organizing committee for this workshop at ICERM in Brown, and this was a week-long in December of 2012, and we brought together a wide group of people, including funding agencies and representatives and people from universities, as well as researchers from a variety of different fields and journal editors. And we spent the week actually brainstorming on this exact question, and we came up with a workshop report that may be interesting to folks in the room around focuses on computational aspects of scientific research and standards for reporting and sharing and making this computational work actually reproducible. Okay, so it's called Setting the Default to Reproducible. Okay, I wanted to mention also that there are many, many tools that by and large, researchers and academics are creating and putting online to help inch towards solutions in their field around reproducibility. And my sense is that tools are what will solve that incentives problem around code sharing and data sharing and make it easier for us to capture the relevant information and share it at publication and before publication. I divided them roughly into 3 overlapping groups. So there seem to be a set of tools around dissemination and dissemination platforms. So Research Compendia, one that I've been working on, IPOL, Madagascar. By the way, these are hot linked and they're all fascinating and wonderful and amazing, and I encourage you to click on some of these links. And so these platforms on how do we actually get work out to the community. So prior to publication is the second group, so workflow tracking in research environments, lots of innovation in how do I work in an environment that makes it easier for me to do reproducible research. And the final category is really embedded publishing, so how do I do better than delivering a static PDF to you? Can I deliver something that has code in it, has data in it, that you can execute or play with some of the figures and the results in the publication itself? Okay, final thing I'll mention, and it was mentioned in the introduction, so I feel like I should touch on it, is there are very serious legal barriers to doing reproducible research. And they're not there on purpose, they're just there as legacy that we need to deal with as a scientific community. One of them is copyright, so sharing code, sharing data. Copyright, as you can see, it's embedded in the Constitution to promote the progress of science, so that's right there in the justification of copyright, and the useful arts by securing for limited times to authors and inventors the exclusive right to their respective research and writings. So any original expression of an idea, it's that original expression that falls under copyright, and it falls under copyright by default. So the work that we do as scientists has very large copyright components to it. Our papers, code, figures, tables, for example, all these original expressions of ideas. However, if we look at what copyright does, so it secures these exclusive rights in the author, so whoever has expressed these ideas, these original ideas, only the author can reproduce the work, and only the author can prepare derivative works based on this original, or the author needs to give permission. And so that is exactly orthogonal to what ideally we would like to happen to our work in science, right? I'd love it if people were able to go out and reproduce my work, or they were interested enough to do that. And prepare derivative works, this is our measure of impact, right? Like people who are creating new scientific discoveries based on the work that I've delivered to the scientific community. A couple of exceptions and limitations to copyright that I haven't mentioned, like fair use, but they don't actually reach out to encompass all of our work as scientists. So I won't build it up because I know we're short on time, but one of the steps that we could take is actually to release our work with pre-permissioning about reuse, reproducibility, and use open licensing. So I suggest a series of licenses depending on the type of work that you're distributing. So creates like your paper, figures, and so on, could go under a Creative Commons attribution license. Code could go under similarly an attribution license like the MIT license. And for reasons I don't have time to go into today, but I advocate putting data into the public domain because it's very complicated. It's a little bit complicated how it interacts with copyright. So this I called the Reproducible Research Standard, and the idea was remove those restrictions on use of code, data, and other aspects of science, and put the way that we use them more in line with our traditional Mertonian norms. Okay, and I'll leave it there, since I know we're short on time, and I think the panel is next. So, thank you.